Welcome to this explainer. Today, we're going to metaphorically throw on our lab coats and act as scientific investigators. Our mission? To decode the absolutely spectacular molecular events happening all around us, every single day.
You know, what's really fascinating here is how this totally reframes our daily lives. We tend to think that complex chemistry only happens in those sterile, multi-million-dollar facilities. But the truth is, your own kitchen is literally a high-stakes laboratory. Every time you boil water for pasta, or, let's be honest, accidentally burn a meal, you're initiating some incredibly complex scientific processes.
Okay, before we can start investigating these changes, we've got to define our baseline playing field, matter. Now in science, matter isn't just stuff. It's anything that has mass and occupies space. And depending on molecular density and kinetic energy, it exists in three primary phases. You've got solids with tight structural integrity like stone, highly adaptable liquids like water, and expanding gases like the air we breathe.
Section 1. The two paths, appearance versus identity.
So we live in a world of constant flux, right? And honestly, the greatest illusion in our universe is mistaking a simple change in appearance for a change in actual identity. Let's dive into our first path, the physical change. This is a transformation where a substance might change its state or its shape, but its internal molecular script remains exactly the same. We're really just changing the spacing between the molecules, not the molecules themselves.
Let's look at a classic example. Think about stirring a sugar cube into a glass of hot tea. The sugar seems to completely vanish right before your eyes. But, as our scientific framework tells us, this is merely a physical distribution, not a chemical destruction. The original sugar solute is completely retained. It's really just wearing a new mask.
Now, the second path is a completely different story. This is the chemical change. This happens when a critical energy threshold is crossed. The actual internal atomic architecture of the material is broken apart and entirely rewritten. You are literally synthesizing a brand new substance with totally different properties.
I like to think of physical changes as a recoverable two-way street. Because no internal bonds were actually broken, you can just use evaporation to remove the water and get your solid sugar right back. But chemical changes, they're an irreversible one-way street. They permanently consume the parent feedstock to create something completely new. Once you cross that energetic threshold, there's no easy way back.
Breaking this down to its core, there is a really rigorous distinction here. Under physical changes, we have zero synthesis, meaning no new substance is produced, and the original molecular identity is perfectly preserved. But under chemical changes, we have product synthesis. This is a full-blown micro-restructuring that births an entirely new material right out of a chemical reaction. Section 2. The Investigator's Toolkit, Diagnosing the Invisible. So this brings us to a pretty profound challenge. I mean, since we obviously can't see atoms breaking and forming with the naked eye, how do we actually prove we've crossed that point of no return? Well, the answer lies in four specific macro signals. These act as our primary diagnostic tools, allowing us to interpret those invisible chemical changes using just our basic senses.
When matter crosses that point of no return, our senses can detect four undeniable indicators: chromatographic shifts, effervescence, precipitate formation, and thermal flux. If you spot even one of these, you aren't just looking at a change in shape, you are witnessing the birth of a new substance.
Let's kick things off with the first signal, a chromatographic shift, which honestly is just a formal way of saying a definitive, unexpected change in color. When a high-tensile gray iron gate is left out in the rain, it doesn't just get dirty. Its atomic structure is entirely rewritten by oxygen, permanently replacing it with the brittle, orange-red compound we all know as rust.
Moving on, the second indicator is effervescence, or gas production. Combustion is a perfect example of this. When you burn wood, the solid material is irreversibly consumed, violently releasing entirely new materials like smoke, ash, and gases into the atmosphere.
Okay, the third signal is precipitate formation. This is a sudden change in solubility where a new solid just unexpectedly appears from a clear liquid. If you've ever had the misfortune of pouring spoiled milk into your morning coffee, you have definitely witnessed this firsthand. That sudden appearance of solid, curdled proteins separating from the liquid? Yeah, that's a chemical reaction confirming a new identity has been formed.
And finally, we have thermal flux. This is a significant enthalpy shift, which is really just a technical way of saying energy is dramatically released or absorbed, and we feel that as heat or light.
Whether it's the intense heat of a roaring campfire or a chemical ice pack getting freezing cold entirely on its own, it confirms that high-energy intramolecular bonds have been violently cleaved and reformed.
Section 3. The real-world stakes. Why this matters.
So you might be wondering, why go through all the trouble of diagnosing these molecular rewrites anyway? Because understanding the fundamental difference between a temporary change in form and a permanent change in essence is literally a blueprint for civilization. It's absolutely critical for understanding natural processes, powering industrial manufacturing, and ensuring safety in our everyday lives.
We actually use physical changes to predict the phase stability of the water cycle, as H2O shifts from ice to water to vapor without ever losing its identity. We use chemical changes to cook our food, permanently rewriting its nutritional essence. And crucially, we rely on predicting these chemical reactions to implement safety protocols, preventing the accidental, irreversible destruction of expensive materials or hazardous outgassing.
Whether you're an engineer or just a home cook, the real professional differentiator in life is having that scientific awareness to look closely at matter. You have to ask yourself, am I observing a temporary change in presentation or a permanent rewrite of fundamental essence? That knowledge is what translates basic observation into precise engineering.
So I want you to look around your own surroundings right now. Try to spot the rust on a gate, the ice melting in your glass, or food sizzling in a pan. Are the changes you see just temporary pauses on a two-way street, or are you witnessing a permanent, irreversible transformation of identity? Once you know how to read the signals, the ordinary world stops being static and becomes a thrilling, dynamic laboratory. Thanks so much for joining me on this explainer. Keep observing and keep questioning.